Welcome back to the AI in Medical Education. Today we have Dr. Seema Singh, who is a general surgeon by training and then went on to pursue her passion in IIM Ahmedabad. And then she is a mentor for many startups. She is having keen interest in AI in medicine and health. To moderate the session, we have Mr. Parag Agarwal, IIT, IIM alumni, having a vast industry experience and then knows what to do and what not to do. Over to you, Seema, to take the topic.
Thank you, Suresh. A very good evening, everyone. I am Dr. Seema Singh, a general surgeon and IIM Ahmedabad alumnus. I am former faculty in general surgery from UCMS Delhi, and currently I am co-founder of a healthcare consulting company. So today we will be talking about a very important and pertinent issue that we face while developing and implementing AI solutions in healthcare. That is the problem of unstructured and missing data. So let me start by sharing my screen. Please let me know when my screen is visible. Is my screen visible?
Yes.
Go ahead, ma'am.
Okay, thank you. So at the outset, I would like to thank NBE, especially Dr. Suresh, for giving me this opportunity. So these are my disclaimers. I'm a general surgeon with a management degree. My experience with AI in healthcare is essentially from working as a domain expert. I am not a coder or a data scientist, so I'll not be talking about any algorithms or codes today. I'll focus only on the basic principles. So before we start talking about unstructured or missing data, let's try and understand why this topic is important. See, we all know that in case of healthcare, AI actually influences a lot of our decisions, from ranging from diagnosis to triage to treatment. While in other fields, any error in AI will only be an inconvenience. In healthcare, it can lead to actual harm. That is why the accuracy of healthcare AI models is far more important than other fields. And that is why data and information purity becomes so much more important in healthcare. Since a lot of data in healthcare is unstructured and some of it is missing, we have to talk about unstructured and missing data before we even talk about valid and relevant AI algorithms. So the learning objectives of the session today would be to understand unstructured and missing data and what is its importance in healthcare AI. We will recognize why missing data is common in healthcare and why it is rarely random. Then we'll talk about methods for handling this missing data. And at the end, most importantly, we'll talk about prevention strategies that are especially relevant for clinicians and to recognize how documentation saves AI. Accordingly, the flow of discussion that I have planned today is we'll be starting with unstructured data. We'll talk about its characteristics, importance, challenges faced in handling unstructured data, and how to handle this data well. Then we'll move on to missing data. We'll understand missing data. We'll look at the classification and relevance of missing data, and briefly talk about how to handle missing data. And we'll end the session with the most important part, that is clinician-led strategies to prevent unstructured and missing data. So let's get started with unstructured data. Before we try to understand what is unstructured data, we need to know what is structured data, obviously. And this holds importance not just in healthcare, but in any field. See, structured data is something which is stored in very neatly labeled rows and columns. This could include numbers, data, strings, etc. This data is very easy for AI algorithms to use. You feed it into an AI algorithm, and an algorithm will straight away use this data to do its predictions. And this requires much less storage. On the contrast, unstructured data is something which is not stored in rows or columns. It is not labeled properly. So this will include your images, your audio data, your video data, spreadsheets, etc. And this data, by its inherent nature, requires a lot of space to store, and also it is very difficult for AI algorithms to use. Now, once we have understood the contrast between the structured and the unstructured data, let's see what real data in healthcare looks like. As you can see from these infographics, it's only 30% of the data in healthcare which is structured. And this would include your patient demographics, lab tests, vital signs, medication records, disease codes like ICD codes, etc. A huge chunk, 70% of data in healthcare is unstructured. This will include your medical imaging data, radiology images, ultrasound images, pathology slides, your waveform data like your EEG, ECG, your doctor's notes, discharge summaries, that is your textual data, and genomic data. So you can see from here that a huge amount of our data is unstructured. So which brings us to the question that a large amount of data is unstructured. This data is very difficult to use for AI. So where do we go from here? Do we just ignore this data and build our AI models only based on structured data? Or do we somehow find ways to use this unstructured data? Well, the answer is no, we cannot ignore this unstructured data. And why? Because this unstructured data, it's a powerhouse of insights. It has very rich and deep insights, gives you a lot of contextual information. Structured data only gives you numbers, doesn't give you the story behind those numbers. It is the unstructured data, the doctor's notes, maybe other observations, maybe procedural notes, discharge summaries, which provide context to the information which is stored elsewhere. So without this contextual information, we cannot use this data for decision making. So that is why using unstructured data is very, very important to provide context to your structured data. And it is this unstructured data which lends itself to more innovation and new products in AI. So that is why we have to use this unstructured data. We just cannot ignore this data mine. So when we have to build AI algorithms or implement AI algorithms, we have to somehow figure out ways to use unstructured data. Now, since we have decided that we are going to use unstructured data for our AI algorithms, we have to be mentally prepared to face some challenges. Now, what are the challenges and why should we know about these? We spoke about in the beginning that unstructured data is huge in size, difficult to store and all. Now, when you decide that in your organization, you are going to build algorithms based on unstructured data, then you have to prepare for that. And these are some of the challenges that I have listed out here. The first challenge is the high storage cost. We know unstructured data because of its nature will require a lot of storage, and storage comes at a cost. Whether you go for a cloud storage or on-prem storage, you have to be prepared to invest in data storage if you want any insights to be drawn from your unstructured data. Second is difficulty in analysis. Unstructured data doesn't lend itself to analysis straight away. It has to be tweaked, it has to be pre-processed, it has to be fed into various kinds of algorithms to be made useful. And obviously, all this needs specialized tools, skills, and people to do. So if you are looking at using unstructured data, be prepared for investing in these tools. Third challenge is time consumption. Unstructured data, because it is complicated to pre-process, will take time for processing and for usability. So in case you're looking at using this data, then have patience because this is a long drawn journey. And the next and the most important challenge that one has to be prepared for is quality related issues. Because this data is not recorded in a structured format, there will always be issues with the quality, as in the missing data or some bad quality data. And its security and compliance will always be a challenge. So even before we decide of to go ahead and build or implement AI models using unstructured data, we have to be very, very sure of ourselves and be prepared to face these challenges and account for them. So then how do you face these challenges? See, using unstructured data requires a very robust data strategy. Is this black box visible or only I can see it? Dr. Suresh?
No, we can see that. We can see that.
But is this actually obstructing the... Let me just stop sharing the screen, share it again. Give me a second.
We can see that. That's not a problem. Seema, you can go ahead, continue.
Okay, sure. It's actually obstructing my view of the slides also. Is the screen visible now?
Yes, very much.
Yeah, sure. Sorry for this interruption. So now that we have decided to use unstructured data, the first and the foremost thing that we have to look at is a very robust data strategy. And a robust data strategy means that we have to plan well in advance and store and use data accordingly. So some of the steps that will constitute a part of a robust data strategy, first and foremost would include storing data at scale. As we discussed, that unstructured data requires more storage. So the storage solution that you're opting for has to be scalable. It has to be able to store huge amounts of data at a minimal cost. Practically speaking, cloud storage solutions work better because they are scalable, flexible, and cost effective. However, the decision to use cloud storage versus on-prem storage is an administrative decision which depends on the organization, but practically speaking, cloud storage works better. The second strategy is to store data in its raw format, what we call as data lakes. It is a better strategy to store unstructured data in as-is form without pre-processing in the form of data lake, so that when you are going to build some algorithm, you should not face the challenge that you have already pre-processed and some of the data is lost and some of the information that you're looking for is not available. So it's better to store data in the raw format, and as in when you need it for specific algorithms, you pre-process it accordingly and extract the information. So that's the first part of the strategy, store data at scale. The second step is using data processing tools. Unstructured data does not lend itself to AI algorithms in as-is format. You have to pre-process it and you have to be ready to use various tools to convert it into a structured format. And some of the common tools that we use include the natural language processing tools, that is NLPs, image recognition tools for images, and audio processing. Now, these tools are something which AI engineers or data scientists will be using. As clinicians, we do not need to be well versed or trained in using these tools. We have to be aware that these are the various tools that are available. Then comes the next step, that is the categorization and analysis. Once unstructured data has been processed using these tools and put into a structured format, that is where the next step, that is tagging this data, labeling it, comes in. Now, what is tagging the data? It is providing names and tags to the data so that AI is able to recognize and read the data. Essentially, metadata tagging is something which converts dark data into an actionable machine learning data. And this is the step where the role for clinicians come in, because we are the people who will help the technologists to actually tag, label, and annotate the data. If we work with AI organizations as domain experts or subject matter experts, this is one of the most important roles that we can play in the life cycle of building AI, that is help with the tagging and annotation of the data. Once the data has been tagged and annotated, then it can be fed into the machine learning algorithms, which can then draw useful insights from the data. So these are the three steps, three basic strategies that are initially needed for making your unstructured data useful. But then this has to be followed by the fourth step, that is merging and integrating your unstructured data with your structured data. Because if you're using two sets of data separately in silos, they will not provide you with the complete picture. Hence, it becomes very, very important to merge all the data before actually using it for any analysis or taking out insights. And needless to say, all this process, all this creating and implementing a data strategy requires cross-functional teams of data scientists, IT specialists, business analysts, and most important, clinicians. So these are some of the steps and the strategies by which you can use your unstructured data. So this was in brief about unstructured data and how it is important and how we can use it. Now we move on to the next part of the session, that is the missing data. And what is the linkage between unstructured and missing data? Also, I will be talking briefly about. So when we try to understand missing data, I tried to create an AI generated idea on how much data in healthcare is actually missing in the current scenario. And this is the image that AI gave me. And the numbers here are significant. Based on simulated ICU data, 10 to 50% of medical monitoring ICU data is missing. 18% of EHR data is missing. A lot of lifestyle and variable data is missing. So these numbers, they just go to show that missing data, even in current times where a lot of data is digitized, missing data is still a significant problem in the AI world. So what is missing data? To define missing data is information that should exist but is absent. For developing a good AI algorithm, this information is very much needed. But when the data pre-processing is done, these fields are found to be empty. So the AI is forced to label this as missing data. Now, how does this missing data occur? First is what we call as a test or a process not done. What do we mean by not done? Is that a procedure or a test or a follow up visit that should have been done so that the patient's record is complete, but it actually did not happen. There can be various reasons for this. Patients may miss a follow up, doctors may not advise all the tests that are required for various reasons. At times, in chaotic environments like ICUs, patients vitals are not taken very regularly. Or for that matter, if the patient is very stable, then also we may not be taking the vital recordings regularly. So there are various reasons where tests, etc., which should have been done and recorded are actually not done. So that's the first form of missing data. The second form is something which is done but not recorded properly. This would include our test reports. If the test reports are not digitized, they are handwritten and they have to be entered into a system. You might miss it in a place like ICU, if the patient is very sick and our preference right then and there is to save the patient, we may be doing recording vitals, but may not be putting that into the system. So these vital readings, even if they are taken, they are not recorded. Similarly, verbal orders from the doctors might be executed, but not actually recorded in the system. And one of the most important data that goes missing in our experience is the outcomes data. When a patient comes for follow-up, let's say following some treatment or some surgical procedure, what is the final outcome is not recorded properly in the system. So even though the data is there, it is missing from a AI systems perspective, essentially because it was not recorded digitally in the system. And the third important type of data that goes missing is your unstructured data. And how does unstructured data go missing? See, it is recorded in free text. There is no structured recording here. And as we discussed earlier, we are using algorithms like NLP to read it, and then further ML algorithms to construct it into a structured format and use it. Till date, the AI algorithms have not grown as reliable that they can completely convert this unstructured data into a AI usable data. So that is where, however good your algorithm is, some of your unstructured data will go missing. Some of the clinically important data will go missing if it is recorded in an unstructured format. So that is why the relevance of unstructured data in AI perspective increases, because a lot of this data ends up being as missing data when we are trying to create the algorithm. So this is how these two types of data, unstructured and missing data, are tied to each other. So now let's look at few of the factors that would lead to missing data. And why I'm talking about factors beforehand is because this is from where we will derive our prevention strategies. So factors, we divide them into three: patient related, clinician related, and system related. So what are the patient related factors? Patients, they may miss their follow-up appointments. There may be some financial barriers. They may not be able to undergo some tests or investigations which are prescribed because of the cost, etc. If a patient is very severely ill, they may not come for testing, they may not come for follow-up. So all these patients, their data will go missing from the overall data that you are going to use. Then comes the clinician related causes. See, we all know how busy clinicians are in their OPDs. While they are looking at the patients, they are maybe looking at 10 different factors, but recording only the final outcome of the diagnosis. See, what AI is trying to do at times, it is trying to reverse engineer a doctor's thought process. A doctor looks at 10 factors to come to a decision and makes treatment decisions accordingly. What AI system does is, by reading a doctor's prescription or doctor's notes, tries to reverse engineer that whole process. But if, as a busy clinician, I have only written the final diagnosis, or the final treatment. I have not documented the other factors that have gone into making that decision. Then that document, when it is fed to AI, the AI will not know the decision making process. It will only know the final decision. So what the algorithm learns will be a half-baked truth. So that is why in busy clinics, if the clinicians are not recording the entire process diligently, that data will go missing for an AI algorithm. At times, we advise tests very selectively. For example, if patient has a poor prognosis or outcome, we will not advise very costly tests. But when the algorithm is getting trained, then the test data goes missing for that patient. So, and unstructured data, free text notes, we already spoke about. These are some of the clinician-related factors due to which data goes missing. Over and above all these are some system and infrastructure related factors. For example, if we are using an EMR, we are as a clinician are using an EMR and putting all the data in a digital format, but EMR itself leaves out some data points, some are optional, some are not very easy to document. Then because of that system only, the data quality is low, we are missing data. At times, our devices fails. Devices that should be integrated, data should be flowing automatically into the EMR. The integration fails and the system fails. So these are some of the reasons why data goes missing in healthcare. And it is from these reasons that we will later be talking about the prevention strategies for preventing missing data. Now, before going any further on how to handle and how to prevent missing data, let's quickly look at how do we classify missing data. Missing data is conventionally classified into three types. First is data that is missing completely at random. Second is data missing at random. And third is missing not at random. Now, what does the first type, that is MCAR, mean? So this is the data where one or two readings they are missing, but there's no specific reason attached to it. It's completely random. For example, a patient was coming for follow-up visit, had a flat tire, couldn't come for the visit. The data for that visit is missing. While the patient is coming for subsequent visit, but that one column, one data is missing. It's completely random. You don't know why it is missing. This is data missing completely at random. Good thing about this is that this does not create much bias in your ultimate outcome. You can simply ignore this data and move ahead with your algorithm. Second type of data is data which is missing at random. Here the data is missing and there is a pattern to this missingness. This data is missing because of some specific reason, and that reason you can figure out from the other parameters that you are collecting. So this is the good thing about this kind of random missingness is that the reason why this data is missing is known to you. Although it is not random, but you can correlate it with the other factors. And what that does, it makes it easier for you to replace or fill in this data based on the other parameters. How we handle this, we'll talk about it later. But this data produces less bias in the AI algorithms because it can be easily addressed by statistical methods. You can replace this data. Then comes the third and the most important type of missing data, that is missing not at random. Now this data is missing. We know this missingness is not random. There is some reason behind this. There is some pattern behind this. But we are not able to figure out that pattern based on other coexisting variables. So that is where this becomes dangerous. We know it is missing because of some specific reason. We do not know the reason. Now, if we do not know the reason, we cannot use simple statistical methods to fill in or replace this data. Otherwise, the outcome that comes out will be very biased. So this is the kind of missingness which introduces the maximum amount of bias in our data. So I'll try to explain these types of missing data with a few clinical examples, and then we will move on how to handle each type of it. Missing completely at random, you advised a blood test, a blood sample was taken, but it was lost using transit. So one or two blood test readings are missing. This is completely random MCAR data. You can ignore this. Missing and random, there are age-related barriers. For example, if you're trying to do a longitudinal study on blood glucose levels of diabetic patients, elderly patients, they may not be coming to you for repeated testing. So a lot of blood glucose data related to elderly patients will be missing. Now, when you look at this data, you know this data is missing and you know the pattern. It is related to another factor, that is age. So if you have recorded the age in your data, you can easily find out this pattern. You can use statistical methods like mean, median to replace this data. So this is not random, but it is controllable randomness where you can replace it. Coming to the MNAR data, this type of data goes missing mostly because of severity. Patients who are severely ill, they will not come for follow-ups, they will not fill in your questionnaires, and their data will be missing. For example, if we are doing a longitudinal study on depression patients, patients who are severely depressed, they will not fill in our questionnaires and will not have any data related to severely ill patients. Now, since the severity is not recorded in your data, you know this data is missing, but you don't know the pattern. So this is an example of missing not at random data. So now that we know that there are three types of missing data, we can move on to see how these three types of data, they are going to impact our AI models. Now, the most challenging part here is that the maximum amount of missing data in healthcare is MNAR, that is missing not at random. Unlike other fields where random missingness is more common, in healthcare, when you talk about missing data, when you study the frequency of missing data, you find that majority of the data that is missing is not random. And even more challenging is the fact that this missingness is most often related to severity of the disease. It is the severely ill patients who will not come from follow-up. It is poor prognosis patients who will not undergo testing done. It is under high stress conditions like ICU where patients are severely ill that documentation will suffer. So a lot of this missingness is actually related to severity of disease, and this is clinically very, very relevant. However, if this is not handled properly, then what happens is when you train an AI algorithm on this data, which has a lot of MNAR data, your AI algorithm learns based on healthier patients. It will only include data of patients who are not that sick because, as we saw, the severity of illness leads to a lot of missing follow-up and missing data. So the algorithm that runs on healthier patients will have a lot of bias. And what that will do is ultimately, if you deploy that algorithm on your real world data, it will give you very, very biased results. So let's look at a few examples here to understand how your missing data is going to impact your AI algorithms. I have taken three very specific examples here. First, look at a diabetes complication prediction. Let's say I am looking at HbA1c data, longitudinal HbA1c data of patients to predict the risk of diabetes-related complications. Now we all know it is the poorly compliant and the high-risk patients who are not coming for follow-ups. It is these patients who would not get their HbA1c done. So the missing HbA1c data would be more related to poor compliant and high-risk patients. Now the algo doesn't know that. Algo will only look at the available HbA1c data and predict risk according to that. So what will happen is that whatever overall risk is predicted will be lower, which means your high risk patients will also be graded as low risk patients because the system has not actually seen high risk patients. It has only seen low risk patients. These are the patients who were regularly coming for checkups. They were very diligent in their follow up. So missing the data of high risk diabetes patients will bias this algorithm. Another example can be for imaging data. When we train AI imaging algorithms, we use very good quality data. We use a lot of data which is available online from free data sources. Those are all very good quality images. So the algorithm gets trained very well. But when it comes to real world, so this is an example where the algorithm has been trained well, but when it comes to implementing it in the real world, because in real world you will have images of all different qualities. So a very well-trained algorithm run on a mixed quality data will again fail because this algorithm has not learned to interpret poor quality images. It will it will fail in your real world where the quality of images is not always very good. So that's where in advanced settings, in advanced disease in real world settings, this algorithm is going to fail. Third very typical example is when you use prediction models in ICU. if you are using vital parameters as, let's say, predicting prognosis or outcomes in ICU, we discussed earlier, ICUs are very chaotic environments. When the patient is really sick, the vitals are not getting recorded properly. So for patients who are more sick, who have poor prognosis, pretty much like the diabetes example that we took, the actual data is not getting recorded. There's a lot of missing data. And the algorithm thus gets trained on less sick patients. So the outcomes that it will give will lead to an underestimation of mortality and morbidity. So that is how this algorithm will fail, because there is a lot of missing data. And you can see in both these diabetes and the ICU prediction model, this missingness is not random. It is essentially related to severity of disease. That is why it has a whole lot of impact on your AI algorithms. So now that we know that a lot of healthcare data is missing, maybe because of various reasons, and this missing data is not random at all, it is mostly related to severity. That is why this data has a lot of impact on our AI algorithms, creating a lot of bias and limiting their reliability, which means this handling this missing data becomes very, very important whenever you are trying to train an AI algorithm or whenever you are trying to implement an AI algorithm in your real world setting. That is how handling of missing data becomes relevant. And how do we handle missing data? So the way we spoke about three levels of missing data, from less complicated, that is missing completely at random, to maximum complicated, that is MNAR data. Similarly, handling will also happen in a very structured, staged way. So the simplest way to handle this missing data is to ignore this data. This is a very simplistic approach where you just delete and ignore the missing data. But this works only for when your missing data is completely at random. You do not expect ignoring this data to introduce any bias, so you just ignore it and move on. When it comes to data, which is the next level of complication, that is missing at random, the MAR data, you have to use some statistical methods to fill this data. Remember, we discussed that MAR data, you know, it is missing because of certain parameters, because of certain patterns, and you are able to figure out those patterns. So by figuring out those patterns, you use simple statistical methods to simply fill that data, and then you can use that data for your AI algorithms. And the next level is, how do you manage data which is missing not at random? Using the filling MNAR data will need the next level of tools, that is your ML models. So you will have to use ML models to understand the nature of randomness, try and correlate with various other factors which may or may not be recorded in your data, and then fill in that data based on the model's outcomes. And even this will not suffice. Will have to make these models context aware. By context aware, we mean layering it with even more information. At times, there's a lot of clinical judgment, or there is a lot of rule-based information which is not fed into the model, but which has to be layered on top of it, so that even these ML models, while filling in gaps in MNAR data, they are far more smarter. So for filling in MNAR data, you will need ML models and essentially make them context aware, which will need more of your deep learning models. And now, as generative AI is progressing more and more, we are looking at various applications of generative AI in filling in this MNAR data. So this is a general approach by which you can handle your missing data, essentially starting from simplistic approaches to your completely at random data to more complicated approaches for your MNAR data. I now add a little bit more detail to these methodologies. Essentially, in this slide, you will see a lot of technical jargon being thrown in. The idea here is not for clinicians to learn these methods or be expert in these methods, but as a doctor, if you are interacting with AI engineers, if you are interacting with data scientists, then you should be aware of some of these terminologies. You should be aware of some of these methods that are commonly being used, so that if somebody throws these terms at you, then you are not clueless about it. So I'll just list out some of these common methods. Ignoring data is what we call as complete case analysis. We go by each case of missing data and as a list, and then we either delete it as a row or delete it as a column depending on how much data is missing. Then we move on to the simple filling, what we know call as imputation of data. This is used for MAR data, and some of the common examples are simple imputation, forward backward fill, and advanced imputation using algorithms like MICE, that is multiple imputation using chain equations. These are simple statistical methods where based on other parameters, you take mean, median, mode, and you fill in the data. Then the most complicated methods are that some of the machine learning models, some of the common examples, and you will hear these terms very often: K nearest neighbor, decision tree models, random forest, expectation maximization for tabular data, and recurrent neural networks and transformer models are for sequential data. Again, to emphasize, as clinicians, we need to be aware that there are various types of algorithms which can be used for handling and filling missing data. We are not, as long as we are not engineers, we are not getting into the technical depths of it. We do not need to be experts of these methodologies. So where does all this bring us to now? We discussed that a lot of data in healthcare is missing. This is MNAR data, but then we also talked about handling approaches. So if the missing data can be handled by ML algorithms, and we all know these algorithms are evolving, then why are we worried about missing data? I think, but some of us might think that the problem has already been solved by AI. The technologies have already become advanced enough to have solved this problem. Then why do we have to worry about? Why are we talking about this missing data today at such an early stage in this uh, course? Well, the answer is that all these context-aware algorithms, however complex or advanced they might be, they still have their limitations. And some of these limitations would be starting with the high computational cost and complexity. These are really complicated models. They need a lot of computational power to run, and they're really complex to implement. So you need very specialized people to run and use these models. More important than that are these two challenges, that is data overfitting and hallucination. A lot of these models, they tend to overfit the data. If they have been trained on limited data, on a biased data, what they will do is they will fit the results onto the entire data set, what we call as data overfitting, and they give out results with a misleading uncertainty. Either they will paint a very rosy picture, or they will paint a very sad picture depending on the data on which they have been trained. So there is a lot of overfitting that happens in these algorithms, which in spite of using algorithms to take care of the data, this is not completely taken care of. So the end results will have a lot of overfitting and the risk of hallucination. This we see very often with generative AI algorithms. They will never say that we do not know the answer. They will give you plausible sounding but incorrect information. This is what we call as hallucination in AI language. So all these models, however advanced they would be, if there is a huge amount of missing data, which is MNAR primarily, they will give you overfitted results and they will hallucinate. So that is why, in spite of all the algorithms being advanced, the dependency on high quality training data still continues. Garbage in, garbage out is something which still holds relevant. If we train data on partial, if we train algorithms on partial data, they will not be able to learn unseen patterns and they will not give you clinically accurate outcomes. So that is why, in spite of all the advances, we still have to believe in the fact that prevention of missing and unstructured data is better than imputation of data. So that is what brings us to the most important part of today's session, that is how do we prevent missing data. See, theoretically, you can say that AI is advancing, I can handle missing data, so let it be. But the truth remains that whatever algorithm you're working, pretty much like the simple biostatistics that we used to do earlier, or the PG thesis that we have done earlier, we all know there is no compromise on the quality of data. So whatever algorithm you might use, you have to play your role as a clinician in maintaining the quality of data. So that is why, in my opinion, this is the most important takeaway message for today's session, that we have to prevent missing data. And how do we prevent missing data? This will need a shift from a reactive statistical fixing, what we have been talking about till now, to proactive data governance. And what data governance means that throughout the entire cycle of model building, from collecting data bedside to pre-processing to using it to implementing it, the quality of data has to be maintained at a very proactive level. So we divide these strategies into two levels. One is the clinician level strategy, where we focus on quality of bedside collection of data, and system level strategy, where we talk about building a. So let me start with the clinician level strategies. As a clinician, we would want you to follow two basic strategies. Okay. First is structure over story. So what does structure over story mean? Is whenever you are recording your data, you prefer a structured approach to recording the data rather than telling a story. You you put your data in discrete format rather than a narrative format. AI cannot read your 3-page note. AI would rather prefer data put in very neat checkboxes and drop downs. So if your EHR gives you the option, then preferably use your drop down menus, your radio buttons. Do not put data in a simple textual format, because free text, as they say, is the primary black hole where clinical data goes to die for AI. So as far as possible, as far as your systems allow you, put everything in a structured format rather than putting in a text format. And another important strategy that we as clinicians can follow is the rule of three. What does rule of three mean? Let's say you are looking at building an AI algorithm for a very specific clinical application. Before you start collecting your data, figure out the top three variables that, in your clinical opinion, are the most important variables for building that algorithm. And then you have to train your team who's collecting the data that these are the non-negotiable fields, at least three non-negotiable fields, which have to be collected in a very, very structured format. So there is no compromise on the most important fields of data. So this is what we call as structure over story. This is the first level of strategy that we as clinicians have to adopt if we are looking at good AI algorithms in future. The second important thing for the clinicians to adopt is no blank fields. And this is what makes you the frontline guard for data integrity. There have to be no blank fields in your data. If in your EHR, even if something is normal or negative, do not leave the field blank. This is what we call as the danger of silent normals. You have to categorically document that this was normal or negative. Never leave a field blank. And another thing that will assist you a lot in having complete data is what we call as the golden hour rule. See, we all know that clinical conditions are very stressful. While we are managing the patient, we are not going to be documenting at the same time. But as far as possible, try and document within 60 minutes of the clinical encounter, because after that, you start forgetting the details, what we call as the decay of memory. So real-time entry, preferably within 60 minutes of the encounter, the strategy of document as you go is what you should follow, so that you don't end up leaving blank fields because you just forgot about the data. And the one more thing which we can use, mainly this will help reduce our own burden, is device sync check. Whatever devices your patient is connected to, make sure that if there is facility of direct connection with your EHR, make sure that they are linked to your patient ID, so that a lot of vitals and a lot of other information flows automatically into the system and blank fields are prevented. So at the clinician level, these are two very, very important strategies. Prefer structure over story. Do not leave any blank fields. Moving on to the next level, that is your system level prevention. So what the system can do over and above the bedside discipline of the clinicians, that it can act as a safety net, which will prevent your data to fall through cracks. So if you are looking at implementing a new EHR, or you are looking at a homegrown EHR, these are some of the features that you can have built it. Hard stop validation. Keep only required fields as mandatory. If you make every field mandatory in an EHR, it leads to a lot of fatigue. So people, because they have to fill too many fields as mandatory, people will not be putting in quality information and the quality of data will go down. So there should be hard stop validation. Automated data capture, as far as possible, all your devices should be connected to EHR and data should be captured automatically. Smart query logic, use cascading questions. If you ask one question, clinician gives a response, then there should be follow-on questions automatically appearing on screen so that the further data entry becomes easier. After the stage of data entry, again, the system is what can become the safety net, the guard. For example, point of entry validation. If a doctor is entering a value which is clinically implausible, the system should be able to flag that. Even after a recording has been done, there should be a program running in the background which flags values which are clinically implausible. For example, a heart rate of 100, and those can be then checked and corrected while the patient is still in the hospital. And the most important is a nudge dashboard. As an administrator, as a hospital in charge, or as a unit in charge, you should have a dashboard where your system is able to give you the missingness scores so that your team has, some goalpost to achieve. There is some impetus for the team to reduce their missingness score and improve the quality of data. So this in a way brings us to the end of the session. Before we end this, I would just like to summarize the key points again. Data integrity in healthcare is very important because of the importance of the AI algorithms in healthcare in decision-making process. However, most of the data in healthcare is unstructured. It is this unstructured data which becomes missing data. And missingness in healthcare is never random. And what does missing data not at random lead to? It introduces a lot of bias and unfairness in the AI algorithms, which leads to performance degradation of these algorithms. Their predictive power and reliability is reduced. And when these algorithms are implemented in real world, what they end up doing is giving you faulty clinical insights. So that is why missing data is very, very impactful in case of healthcare. And what we need to do is prevention is better than imputation. It is we as clinicians who will be shaping the AI safety for future. We should avoid missing data. Starting at the point of care, our documentation habits matter. And to end it all, I'm quoting an AI generated quote. An AI is only as smart as its last meal. If we feed it holes, it provides hallucinations. Thank you.
Wonderful, Dr. Seema. Thank you very much. You and then Parag. Probably, Parag, we can just start our discussion and moderation. And Seema, stay online. Help us in just getting us the answers. Parag, you can unmute yourself.
Thank you
So
so
I
much.
see close to 1,900 questions, out of which at least 300 are relevant to us. I can't ask all those questions. We have left with only 10 minutes time. It's a wonderful lecture. And first question, quick answers so that we use our time the best. Can we change the unstructured data to structured data? Yes, no, how?
Yes, I think we discussed in the initial slides, there are ways of changing your unstructured data into structured data, especially using algorithms like NLP. I'll just give an example. If you have a discharge summary, for example, which is in the form of a PDF, which is free text, you can run a natural language processing algorithm on top of it, which would classify the information into neatly labeled columns. However, as we also discussed, these algorithms are still not 100%. They will maybe do it to a 90%. With generative AI, this is increasing, but we still have a long way to go. But the short answer is yes, you can do it, although it will still not be 100% perfect.
Parag, can you read the next question, please?
Yeah. Actually, the next question, experience which you want to share, because a lot of people, this is about practical, for the clinicians, much about the data scientists on this particular part. What have you seen as a clinician and as a somebody who has implemented AI algo in these decision making? What has been your personal experience? Any thing which you'll want to share with the group?
So I'll just share a very brief example. So I was working with a company which was working on creating an AI model for predicting antimicrobial sensitivity. So what we had with us was culture and sensitivity data from a large tertiary hospital, huge amounts of data, around millions of data points. And when we ran the algorithm on top of it data, what we realized is that there was a lot of culture sensitivity data available, but there was a lot of context that was missing here. For example, as a microbiologist, if I get a sample and I have to decide what antibiotics to test for, I will not by default test the antibiotics which are known to be not working on that bacteria. So that set of entire antibiotic is missing from that list. Then we have a kind of escalation matrix. You will not test high-end antibiotics in the first go. So that second set of high-end antibiotics is missing. But when you feed this data into an AI algorithm without any context, the AI will see that, out of the 20 antibiotics, for 10 antibiotics, the data is missing. While you as a clinician know why it is missing, the algorithm will not know why it is missing. So that became a huge factor for an algorithm to learn. So that is where I mentioned earlier also adding clinical context becomes important. A lot of our thinking, a lot of our prior knowledge is not actually there in the data tables. So when you are converting your data, when you're running an algorithm, you have to provide a lot of clinical context. So this is one of the challenges that we faced while we were working with the culture sensitivity data.
Mhm. Another question, how can missing data be incorporated or handled reliably? Everyone seems to have this thing that, okay, we understand missing data, we understand the unstructured data, but how do you incorporate it without actually bringing in the bias? And, and there is another big concern raised that does it mean that we need to order more and more tests so that all the information is there and there is no missing data?
See, how do we prevent missing data from here onwards is one aspect. In the current scenario, you first is, practically when you go to the ground, you try and hunt for the data. Okay, let's say we're trying to implement an AI system in a hospital, and you look at let's say you go to the electronic medical record, that is the EMR, and you find that a lot of demographic data is missing. Patient's address is missing, it's not there in the EMR. But then you go hunting in the hospital, where can I find this data? A lot of our hospital data is in silos. One system will not talk to another. And one of the hospitals, in government hospital, we ended up at the registration counter. So patient's name, age, gender, address, PIN code, everything was available in some other system. So data which was missing in one system was actually available in some other system within the hospital. So that is why integrating data, looking at data from all the sources is important. So some of your missing data you might be able to find. And this is something which, you will learn only when you have worked with 5, 10 hospitals, where to find which data. That is one part. Second thing is imputing missing data. If it is, as we discussed, if it is missing not at random, you know the pattern, you can fill it using statistical methods. For not at random data, some of it you will have to use AI algorithms. And that is where the talk about contextual awareness comes in. If we are not ordering a test, then it should be documented that this test was not ordered because of this reason. So it should be documented that it was not ordered or it was not done. The more and more context that we keep recording in our data is what will make the data, what will make this more smarter. As I gave the example of these culture sensitivity, if you are not testing a particular antibiotic, then rather than leaving that as blank and the system then reading it as resistant or maybe sensitive, you have to have a way of documenting that this was not done for specific reason. So the more context you provide to your algorithms, the more they become smarter. So one way of handling this missing data is also to provide layering of clinical context. And that is where it becomes important for clinicians to work with AI engineers. If you'll give the data to an AI engineer and just let them do it in an unsupervised way, it will throw errors. That is where the role of clinicians come in, to provide that layer of our judgment, our knowledge to be fed into the algorithm before it starts spitting out the predictions.
See, one of the other concerns which everyone has, so while everyone has heard about AI, everyone uses GPT and likes very well, but everyone is concerned about AI hallucination. You talked about AI hallucination in the last that what Gemini said, you feed it holes and it provides you hallucinations. Now, how do you know that the data which you are getting as of today is reliable, or the AI information which is coming to you is reliable? And when you're processing the data, that AI is not hallucinating in replacing the missing data.
So this is something which I, as a clinician, always say to my startup co-founders, and much to the not their liking. If I see a result from an AI which does not sit well with my clinician's logic, I am not going to accept it. This may not sound very data oriented or very scientific, but as a clinician, if the AI algorithm tells me something which is against my clinician's intuition or logic, I'm not going to accept it. And then that is when I am going to go back to my data scientist, asking them to dig back. And this is something which I have done with some of the startups. The results that the AI algorithm threw, I will not blindly accept it. I will subject it to my existing knowledge, my existing logic, and even only when I'm satisfied, I'll accept it. So this is how, if we as clinicians start questioning it today, we will be having better and more accuracy tomorrow. So everything that AI throws out, at least I, as somebody who has worked extensively, and I think Suresh will kind of agree to what I'm saying, please do question.
Correct. Absolutely.
Mhm. Another question. See, we talked about, the clinicians are very concerned about their autonomy, right? What is, I have been trained to act in a certain way. I'm not here to feed data, right? I'm here to treat patients. As a clinician, I'm not here to feed data, but I'm required by my organization or as a good practice to it. How do you balance clinical autonomy, independence, and AI dependency in terms of feeding as well as referring back to AI? When it comes to clinicians working on the field, on the ground, in the OPD, what is your take there? Can I check every other box? Can I write everything down?
See, that is why when we spoke about preventive strategy, we did not put the whole burden on clinicians. A system level check is also important. We have all heard about this, recording fatigue. That is where EMRs have to be smarter. That some of the information that a lot of information they should be able to ingest on their own. Not all the fields have to be mandatory. And if in case you're working on like we talked about the rule of three, in case you're working on a very specific algorithm, then you choose your priorities, choose those three fields where you have to collect good data. So as clinicians, see, for example, when a blood report comes to us, as a clinician, I know these are the 4 or 5 parameters that I have to look at, and others I, over the time, learn to ignore. So we all know clinically what is the relative importance of data. So there is a Pareto's rule that we call 80-20. So 20% of data will be sufficient to drive 80% of your AI intelligence. So there should be some fields which are non-negotiable. For example, for diabetics, HbA1c is non-negotiable. For a diabetic, a lipid profile may or may not be, as an example, that relevant. So you have to prioritize your administration, your systems have to be in sync with the clinicians. So that is where the burden of having good data is not just on the clinician, that you ask the clinician to fill in 100 fields. Sorry, that will not work. As a system manager, as an administrator, you have to sit with your clinicians and figure out, okay, I can live with this 20% of data because it will suffice for 80% of my future applications. So that's where prioritization and working together as a team has to come in.
One,
We can
something,
take
and
one
maybe
last
the
question, Parag.
last question. Yes, Suresh, Dr. Suresh, last question. Some confusion still exists between MAR versus MNAR. These are because this is something also related to how and what you record, and and in hindsight, you go back and look at MAR and MNAR. So if you can throw some quick light with one example again, so that we close it, with some clarity on these two.
So essentially, both MAR and MNAR are data which are missing not at random. That is one thing which is common. But MAR is something where the pattern is very, very, obvious and visible, and the existing variables within your data are able to explain. For example, you are collecting data for let's say, blood sugar levels. You're collecting the age, you're collecting the gender, you're collecting the blood sugar levels. And you see that some blood sugar levels are missing. And by retrospective analysis, you can correlate that this is correlated to age. So then this data is missing not missing at random, but you know why it is missing. That factor which was responsible for this missingness is there in your data. So then it becomes easy for you to maybe use a mean or a median of the existing data for elderly patients and then fill the gaps. But MNAR, on the other hand, you know it is not missing at random. There is some reason to this missingness, but that reason is nowhere recorded. So you know there is a pattern. So many patients cannot be missing their blood tests or something just at random. If out of 1,500 patients are missing, it is not random because the frequency is far too high. But you are not able to figure out that randomness based on straight away at the simple statistical analysis. That is where the role of ML models comes in, because then these models, they do a lot more in-depth analysis, looking at what more peripheral information or maybe some context which is provided by the clinician separately. So they do a much more complicated calculation to fill that data. And even then, as we discussed, it is not 100%. So that is where MNAR is far more complicated, because the pattern is there and you can't see it. So that's why it is more challenging and complicated.
Thank you.
Thank you very
Thank you so
much.
much. Over
Thank
to
you
you,
very
Dr.
much, Parag, and then Seema. It's wonderful. We got a great feedback and a lot more questions. We are extremely sorry for not taking all the questions. We have a very limited 15-20 minutes to cover up. But Parag did in summarizing most of them, and thanks to the tools that help us. Seema, it's so really wonderful. Before we wind up, for all the listeners, I'll have a few more announcements for you. Please do not use the YouTube chat box for attendance. So the moment you log in from your link, it is automatically marked. Okay. So you watching on YouTube is not equal to attendance. And feedbacks link will open once the lecture is over. And there are questions, and these questions are not pass fail. Okay, it's not a question, it's not like a test. You need to just attend 75%. We are trying to revise it to 60% of attendance mandatory to get the certificate. So don't worry about the attendance. Enjoy the lectures. That's more important. We have wonderful lectures lined up now also, and whatever you heard. And we just want to tell once again that we are learning from the feedback that you people have provided. So please do keep giving us the feedback, both in the feedback forms as well as on the chat also. And next lecture is going to be prompt engineering. That means you people are going to listen how to ask the right set of questions to the AI engine so that we don't err in the wrong places. And we have reopened the registrations. So if your friends, some of them are missing, they can still register. They can still complete 60-75% of the attendance. These are the few housekeeping announcements which I want to just tell before we just wind up. Thank you so very much, Seema, and thank you very much, Parag. So it was a wonderful
Suresh.
lecture and then moderation. Thanks for
Thank you,
sparing your
Suresh.
time.
Thanks a lot. Thank you.
Thank you, Parag sir, and thank you, Dr. Seema ma'am, and thank you, Dr. Suresh sir, for this wonderful session. Thank you, all of you. Thank you so much.
So we're winding up.
Thank you. Thanks, everyone.
Thanks, everyone.